proper welcome time. Okay, so, well, good evening, everyone, and welcome to this tech talk on Hack. So, my name is Damien. You may recognize that from a lot of emails I sent all of you inviting you here tonight. Thank you all so much for coming. Sorry, it's like Peter is now taking a photo of me. That's super distracting. So this is going to be a really fun event. Hopefully, you've all heard of Hack. Actually, who has never heard of Hack? Yay, we have like... I don't believe you. So this talk is actually going to be less about Hack the language and more about what makes the implementation of Hack interesting and cool, and hopefully that will be of interest to everyone. We have a lot of Facebookers here today, so if everyone who's from Facebook can like wave. There we go. So after this talk, we're going to have like plenty of time to like meet everyone from Facebook, socialize, have a few drinks. So I encourage you to like stick around and chat. So without further ado, let me introduce Josh, who is on the Hack team, and who'll be talking about Heresy, apparently, combining type systems with PHP.
Thanks. So hi, my name's Josh Watsman. I'm an engineer on the Hack team, and I'm here to talk about Heresy, combining type systems with PHP. In particular, a lot of the edge cases of adding a type system to a language like PHP, and the sort of things that we have to do to make it all hang together and work well. So this talk is going to have three major parts. First, I'm going to give an introduction to Hack and PHP, for those of you that might not be intimately familiar with the languages. Then I'm going to talk about the Hack type system. The type system is one of the major features of Hack that it has beyond PHP. I'm talking about the Hack type system and a lot of the things that we had to do in order to make the type system hang together well when we bolted it onto PHP. And then I'm going to talk about the actual implementation of the Hack type checker and how that works, and in particular how it can type check code quickly at Facebook scale. So first, what is Hack? Hack is a dialect of PHP developed at Facebook. Among many other features that it has a type system, and in particular that type system is gradually typed. That means that there might be missing type information in different places that we aren't going to be able to infer, or that we don't infer. The reason that we could have missing information is because the type system and the language is fully interoperable and backwards compatible with PHP. PHP doesn't have much of a type system, and so in places when you're interoperating with PHP code, we're going to be missing that information. And so our type system has to be designed to be able to deal with that. Hack is also tied with Go for worst or least Googleable name for a programming language ever. It has lots of other cool features, such as async functions, short lambdas, 1.5 million other things that I won't be talking about or touching on at all today. And you can go to hacklang.org to see the full details of the language. I'm going to be focusing on just one feature, which is the type system. A couple more important points about Hack. It runs Facebook.com right now and has for a year and a half or more. Facebook.com is tens of millions of lines of code. It's not just like some small bit of thing. It is our front end. Hack was designed to increase developer productivity. People have been asking as I'm talking around here if it's about perf or this, that, or the other. And yeah, those are some nice benefits that we can get. But it was about developer efficiency and improving the way our engineers here at Facebook write code. Basically, types matter to Facebook. We believe they help prevent bugs and make our engineers more productive. And so that's why we have a type system in our primary language here. So I've been talking about Hack in contrast to PHP. So let's talk a little bit about PHP. PHP is, as you probably know, a dynamic scripting language for web development. For the purposes of this talk, one of its important features or non-features is that it has a very, very loose type system, and I can barely even say type system with a straight face here. It's a super dynamic language, and there really isn't much in the way of a type system there. I'll call out specific details and edge cases and gotchas as they become relevant. I don't really assume a whole lot of detailed knowledge in the PHP language here, so don't worry about it if you're not familiar with it. So let's look at an example of some Hack code and some PHP code. On the left is a pretty standard bit of PHP code, a pretty standard PHP script. It's going to define a function increment. The increment function is going to take a variable x and return x plus 1. And then a function f, which is going to call the increment function with the constant 42 and echo that back out. So if I were to call the function f in this script, it would echo 43 as you might expect. Any sort of like C or Algol syntax derived language with a few extra dollar signs. Here's what the corresponding hack code looks like. I've changed the opening tag from $PHP to $HH to indicate that this is a hack script instead of a PHP script. There's also a couple of extras here. I have the integer type annotations. The increment function takes an int and returns an int, and the function f returns void. But the main syntax of the language hasn't really changed. Hack is a dialect of PHP. It was developed out of PHP, and so most of the syntax of the language like this is identical. If you know PHP, you're going to know hack. So PHP. This is, at least in my mind, a pretty iconic image, the PHP double-clawed hammer, built by a guy named Ian Baker. He made this photograph. The idea for this came out of a rant that someone whose name escapes me right now wrote, called PHP, a fractal of bad design. PHP is a language that people love to hate on. But for as much flack as the language gets, it has several features that we think have really, really served Facebook well. And when we were designing the hack language, we wanted to make sure that we preserved in PHP as we went into hack. One of the major features that PHP has that makes it nice to work with is a request isolation model. When you start a request, you have a blank slate. You fetch things, and you might persist things to a database, but anything that you don't explicitly persist is thrown away at the end of the request, and you start with a blank slate again at the next request. No shared mutable state or anything like that between requests. But more importantly in my mind, and extremely important for the purposes of this talk, is that PHP has a really fast iteration cycle. I write code in a PHP script in my editor, IDE, whatever you want to use. I hit save, I tab to my browser, and I hit refresh. And my changes, they're there immediately. There's no lengthy compilation step, no lengthy type checking step, nothing like that. You see your changes immediately. And this super, super fast iteration cycle has served Facebook really well to let our engineers be super productive, write code, fix problems, and so forth with nothing getting in the way. And this includes nothing getting in the way, including a type checking step, such as the type system that hack might have. And so a requirement for that was a really fast type checker and type system, which is a lot of what I'm going to be getting to in the third part of the talk, how we make that fast. So that brings me back to hack. Here is the most important thing to keep in mind about hack. Pragmatism. So important that I went out of my keynote presentation into PowerPoint, got some obnoxious word art, found an obnoxious animation, and put it on this slide. Pragmatism. Hack is what happens when you try and shoehorn a type system onto an existing language, onto PHP. We wanted to preserve the body of knowledge that our engineers had about how to write PHP. We wanted to be able to type idiomatic code. And so that means there are some corner cases and sometimes some unpleasant or suboptimal things that we have to do in order to make this all fit together. It's great ideas from academia and that world about type systems applied, again, in sometimes unpleasant ways to an existing language and existing bodies of code, such that we can type check idiomatic code in PHP and in hack. But it seems to work pretty well. We have tens of millions of lines of code in our web front end. Anecdotally, our engineers here really seem to like it and think that it increases their productivity. And so, as an absurd an idea as this might sound, at least I think it seems to hang together pretty well. And from what I've talked to, other folks seem to think the same as well. Okay, so obligatory who are we slides. This is Julian. He's sitting over there. This whole absurd idea was all his fault. He has a master's degree in type theory and very much comes from the academia world. He has experience doing model checking, static analysis, and that sort of thing, and has been doing this for quite a while. So he's coming at this from the programming languages side of things and the academia side of things. On the other hand, there's me. No picture. I'm right here. You can look over at my face. I don't come from a background like that. I have an undergraduate degree in computer science, dabbled a little bit in type systems, but that wasn't really my focus when I was in school. I don't have any sort of advanced degree or anything like that. I come from the world of PHP software engineering. I come from the world of newsfeed at Facebook. Seeing the ways that PHP was super productive and super nice to work with in some cases, and really painful to work with in some other cases, and trying to help hack bridge the gap between that, to make a language that keeps the nice things of PHP, but continues to improve upon it. This is not just a two-man show. Here's everyone else, at least that I could think of, that has made significant contributions to the type checker. I've probably forgotten someone. If you're looking at this and you're not on here, I apologize. This is Jez, Dwayne, Eugene, Drew, Alok, and Casper, several of whom are here tonight to talk to as well. Okay, so now I'm going to spend a bunch of time talking about the hack type system, the ways we type code, and some of the edge cases and other details and nits that you might not have thought about. So a few things to keep in mind as I go through this. First is everything is only one step away, and let me explain what I mean by that. We don't do global inference in any of the code. We do local inference, but no global inference. If a type annotation is missing on a function parameter or function return type, we assume the programmer knows what they're doing. We don't attempt to infer it. We let it unify with anything. We let it pass as anything else. Again, this is because we're typing code that already exists. We can't require annotations to be everywhere because they're not in PHP. PHP doesn't have a type system like this. But we also can't do global inference for a bunch of reasons, most of which come down to performance. They'll be talking about in the third section. So everything is only one step away. If an annotation is missing on a parameter or a return type, we don't infer it. And that leads to some of the interesting edge cases we'll be talking about in a minute. Again, the pragmatism of hack. A lot of the features and examples I'm going to be going through here are to let you just write idiomatic code. You know, you can design a language that's really nice to type. We didn't have that luxury. We had a language that was already existing. And so we have to type the existing idioms that people are used to there. There's also lots of interesting edge cases that PHP gives us to deal with. As a final point, there's going to be no inference rules and no proofs in this talk. We care about formal proofs in the sense that we care that the type systems and the type theory that we're using has been well researched in academia, and that we are then building on that and putting it together. But we also don't care about them in the sense that we're not going to spend a year to sit down and prove our type system sound. That's not a very pragmatic way, at least in our view, of looking at things. So we have a type system that we believe hangs together, and if we find bugs in it, we're going to fix them. But we don't have any formal proofs of the type system beyond the pieces that we are borrowing from academia. Okay, so let's go into a bunch of examples of how we type idiomatic code in hack. So first, how do we deal with scoping? PHP, and therefore hack, doesn't have variable declarations. So let's look at this bit of hack code. We have this function f. We want it to return an int, and we want to be able to check that. X equals 1, return x. So how do we check if x is actually an int? We don't have a type declared for x. We don't have a declaration declared for x at all, as a matter of fact. So we sort of do the obvious thing here. We see a write to a variable that doesn't exist. Okay, that variable exists now. It has type int because 1 has type int. Then you return it, and we can check int is compatible with int. This is really straightforward. Slightly more complicated, but still not particularly complicated, if we have conditionals. We should be able to, this is pretty idiomatic code. I'm not going to pre-declare x, but we should be able to sort of declare x because it's declared in both branches of the if block, of the if conditional. And that's exactly what we do. It's type int in the true block. You write to it, it's an int. In the else block, you write to it, it's an int. Therefore, when you come out, it exists and it's an int in both branches. You come out, it exists and it's an int outside the function. Okay, again, fairly straightforward. Very slightly less straightforward, but still pretty easy. Again, idiomatic code. I expect to be able to, have x defined at the end of this conditional because one of the branches is terminal, and that's exactly what we do. We see x is written as an int in one, it's terminal in the other, and therefore x exists, and it's an int when we come out of the if-else block. Nothing particularly complicated here, but it gets hairier as we keep going. And unresolved types is one of the ways that it gets hairier. Unresolved is how we deal with type inference with implicit subtyping. For those of you that are really familiar with the details of type systems, you might know that general global type inference, when you have implicit subtyping, is undecidable. And so unresolved types is how we sort of designed the hack type system to not run into that undecidability. So what do we do here? Here's another if-else conditional. But in this case, the if and the else don't have x being the same type. So we're going to start off doing the sort of thing we did before. X is going to be an A here, and X is going to be a B here. But the crux of the issue is, what is the type of X whenever we come out of this if-else conditional? And in particular, what type do we pick such that it may or may not pass thing, the return type annotation here, if that's appropriate? Maybe thing is a superclass of both A and B, in which case, okay, thing is the right type for X. Maybe thing is an interface that A and B both implement, in which case we should pick that interface, but how do we know that it's supposed to be that interface as opposed to any other interface that A and B might have in common? And so how we deal with this and what type we infer for X is, well, we actually delay the inference here. We say X is unresolved of A and B. We don't know which it is, so we're going to record both of them when we come out of the if-else block. Then when I hit the return type, I can resolve the unresolved. I can check A against thing, B against thing, make sure they both work. At that point, the type of X becomes thing, because that's the annotation you wrote down, and we can just delay the inference until we hit the annotation. This comes back to what I said a minute ago about everything being only one step away. Total type inference with implicit subtyping is undecidable only when there's total type inference, and we don't have total type inference. You're always going to either hit an annotation, like the thing annotation that I have in this example, or you're going to hit a place the annotation should be and one's missing, in which case we don't try and infer it, we just say, I guess you know what you're doing, and move on. Again, pragmatism. Like, people are laughing, like, I understand where that comes from, but it's the pragmatism of hack, right? We try and type code best we can for interoperability with PHP, and sometimes that isn't always possible, and so we do the best we can. So unresolved types here. We're sort of using something that, again, if you're familiar with type systems, this looks a little bit like a union type. X is both A and B. But as my further examples will show, that isn't really the right way of looking at it. Unresolved is sort of its own special beast. So let's look at this example. Before I go into the types, let me take a minute to explain this. So vector is a collection type in hack. It's a list of items. And in particular, it's a generic type, and so we can have a vector of mixed is my return type annotation here, meaning that this vector contains items of type mixed. Mixed is a supertype of everything in hack. Anything is a mixed. And so this vector could contain anything. On the first line of the function, I say v equals vector curly curly. That's just initializing an empty vector. And then this v square bracket syntax is the append operator in PHP. So I'm going to create an empty vector, I'm going to append the integer 1, I'm going to append the string high test, and then I'm going to return the vector. We can see by inspection looking at this that this should work. This is a vector of mix, the vector can contain anything. And in particular, the anything it can contain can be an int or a string. But how do we actually do the inference here? We don't know when we create the vector what the type of this vector is. And in particular, we do inference on generics, so the programmer isn't telling us this is intended to be a vector of mixed. We're expected to infer that. And so how does that inference work? Well, we can use unresolved types to delay figuring out what the type of the $v actually is. So we start out, we say this is vector of unresolved of empty list. That this unresolved, it's going to grow as I go, but we don't know what this is a vector of yet. Then when I append the int, well, it's a vector of unresolved. I can put the int into this list of unresolved as I go, and then when I do append the string, this is now vector of unresolved of int string. This unresolved keeps growing as I append more things into this vector, and as I continue to figure out more things about the type of this vector. Then I'm going to hit the return $v, and I'm going to check int against mixed, string against mixed, same as I did before, and see, yes, this actually does work. As an aside, for those of you who are familiar with full like Henle-Miller type inference and the way unification and type variables work, there is a type variable alpha around this unresolved. It works in the usual way of type variables unification. I'm just skipping it on this slide for purposes of simplicity. For those that aren't familiar with that, don't worry about it. So the unresolved was growing in my last example, which looks a little bit less like a union type because it grows. Union types don't usually do that. Here's another example where it looks even less like that. So I'm going to do something similar here as I infer the type of this vector again. Unresolved, unresolved of int string is going to continue to grow. But in this case, I'm not returning the vector. I'm passing an in to this function m. Again, in technical terms, it's going in a covariant, or excuse me, a contravariant instead of a covariant position. That means this function m, it's taking this vector as a parameter. It could mutate the vector. It could add something in it that isn't an int or a string. It could add a bool, for example. Since this is typed as vector of mixed, it's allowed to do that. And so when we come back from this function m, saying this is just to enter string isn't really the right thing to do anymore. We passed it into a contravariant position. We passed it to another function, which could have mutated it, added more things to it. So we can't say enter string anymore. We have to actually resolve the unresolved down to the type of the annotation that you wrote and say this isn't unresolved anymore. It's resolved to vector of mixed, such that we then keep the fact, okay, this is mixed. It might have bools or floats or anything else like that in it. It's mixed. We have to resolve the unresolved. And this is actually slightly observable even in the PHP code, depending on how exactly you type things and what error messages you might get, that this type actually changes as a result of this function call. This doesn't look anything like union types anymore. And so, yeah, unresolved is definitely not a union type. Okay. I'll talk a little bit about Hack's flow sensitivity, which is a feature we have to let you type idiomatic language constructs. So let's look at this example. I want to have a function f that takes a nullable int. That's what the question mark means there in the parameter type. And it returns a non-nullable int, since types in Hack are not nullable by default. The way you might think to do this is like, okay, if I get something that isn't null, let's just use that. If I get null, let's use a default value. That's a pretty standard idiom. And so we want to be able to type check that in Hack, and it turns out that this is the code that you'd write to do what I just described, and we can type check this. We can look and say, if x is not equal to null, we actually can change the type of x as a result of this control flow, and say, we understand this sort of check. Inside this if branch, x can't be null. That's what the if test is testing. And so locally inside the true branch of this if, we say x is of type int, and we allow it to be returned there, and this works. Let's just type the idiomatic code like you might expect with the conditionals here. We have more constructs that we're familiar with. So let's take a look at this example. We have a class C and D, which both implement the interface I, but only the class C implements the function foo. Excuse me. Only C implements the function foo. We have this function f, which takes something, and all we know about it is it implements the interface I. But let's suppose for some reason we want to call foo on it, if it's actually a C. In PHP, you just say if instance of and then call the foo. And as a matter of fact, Hack understands this. We understand the instance of test, and we can change the type of x locally inside the true branch of that if to say x is of type C and let you make this call. Again, nothing particularly complicated, just flow sensitivity lets us type idiomatic code. Again, coming back to the pragmatism of Hack. So the next step of this is what we call fake locals. It's how we do this flow sensitivity whenever we have member variables involved. And so here's an example of what I mean here. This is similar to my null check example a moment ago, where we want to return a default value or to use it if it's not null. But instead of being a parameter, it's now a private member variable on the class. We want to do something similar here. We want to say inside this if test that changes the type of the local variable here, but we can't just go change the type, or not of local, sorry, change the type of the member variable. But we can't just go change the type of the member variable. That's a property of the class. We can't like change it everywhere. It doesn't make any sense. We need to change it locally, but it's not a local. So what we do is, well, we sort of fake promote it into local scope and treat it sort of like a local, and then do the same sort of conditioning that we did before. And this is what's called a fake local. It's not really local, but for the purposes of typing, we kind of sort of import it into local scope so that we can conditions type like this. But fake locals behave a little bit differently than other locals, and here's an example. Unlike my previous slide, this one is a type error. All I've done is inserted the call to the function foo here inside the true branch of this if. So why is this a type error? What's going on here? The crux of the issue is that I could have this function defined on the class C. And this function foo might have a reference to the current object when we call foo, and it might call gotcha on it and reset this arrow x back to null before you get a chance to use it on the error line. We have to potentially account for this. We don't know whether it does that or not. We don't have global inference. We're doing everything locally. Everything is one step away. So we have to assume the worst that might happen. And so fake locals, everything we know about them, has to be thrown away whenever we make function calls like this. And so this is a type error as it should be. I'll take questions at the end. Let me finish getting through this. Sorry, I forgot to say that at the beginning. So now let's talk about another process called integration, which is how we deal with sort of another, how we deal with non-local control flow, basically, in particular how that works in PHP. The main feature for integration I want to talk about is try-catch blocks. So here's some code that should work, and as a matter of fact, this does type check. I'm going to have a function. I'm going to initialize the variable x to 3.14. It's a float. Okay, now I'm going to go inside the try block. I'm going to reticulate splines. Then I'm going to write an integer into the variable x, and that's going to work. I'm going to go frog blast the event core. Then I am going to return x. X is still an int. That's compatible with my return type. That works. Now I'm going to type check the catch block. I'm going to return 0. 0 is an int, and so that works as well. Great. Everything works out well here. What about this code? All I've done here is change the return in the catch block from the literal 0 to return x. This is going to be a type error, as it should. And let's look at why. Well, what is the type of x inside this catch block? It depends on how I got there. Maybe I threw an exception when I was reticulating splines, in which case I'm going to jump straight from there to there. Maybe I got an exception when I was frog blasting the event core, in which case I'm going to jump straight from there to there. And the type of x might vary, depending on where I was at the time. So how do we type check this? What do we track in order to make sure that my previous example works and this one doesn't? We actually track 2 types for each local variable. We track the current type, which is the type that it is if control flow is not interrupted. We also track all of the types that it's been inside this function, which is the type that we use if you land in a catch block. And as we're going to see, we use unresolved types for that to get the benefits of sort of the union-ish version of it. And actually, unresolved is the right thing to do here. Let me go through an example. So we're going to track 2 types for each local, like I said. I'm going to write this on the slide as a tuple. The current type, uninterrupted control flow on the left. All types, if control flow were to be interrupted, on the right. So we're going to start with this x equals 3.14. The current type of x is going to be a float. Well, the same as my last example. Sure, and it better be. But the list of all types is going to be unresolved of float. Again, unresolved types here because there are going to be many things here, and we're going to use it if we get to the catch block. As we continue going, I'm going to say, okay, x equals 42. The type of x is now an int if control flow is not interrupted. But the list of all types it's been is unresolved of float int. It could potentially be either one, depending on where we get interrupted now. And the process of adding new variables into this unresolved is integration, is the name we gave it. Not super important, but hence the title of the slide. Then we're going to frog blast the event core, go to this return x. The current type of x, the type on the left, is still int. That's the one that matters here. Int is compatible with int, and this line of code will not be a type error. But the next one will be. When we land in the catch block, we're going to flip the right-hand side over to the left. Control flow has been potentially interrupted at this point, when we're inside the catch block. And so the current type of the variable is, well, any one of the types that it's been through the rest of this function. And so x is going to be unresolved float int, and float is not compatible with int and hack, and hence this error. The next type I want to talk about is a type we call this, which is how we deal with method call chaining. Again, another common idiom in PHP and in hack. So here's the crux of the problem. I have 2 classes, C and D. C implements the function foo. It's going to presumably do some mutation and return $this. D is going to be a subclass of that, have the function bar, presumably do some computation, and return this. What I would like to do is have the function f instantiate a new D, call foo, then bar, in line like this. Again, for those of you that don't write a whole lot of PHP, this is a really common idiom in PHP, and probably in other languages too, but especially in PHP. But this isn't going to work. So D arrow foo, that first call, that's allowed. The function foo is defined on D because it's a subclass of C. But the function foo here is typed to return C. And arrow bar, that's not allowed on something of type C. We've forgotten the fact that we had a D all along. And all these things are returning this, and we should be able to keep track of that, but we don't. So what type do we write here? What does foo and bar return? Well, in particular, what does foo return? We can't write C there for the reason I have on this slide. we can't write D there because, well, it might not return a D if I actually do have a C or something, some other subclass of C. And so we have a type that we call this, which is the type of $this. The type of this is filled in at the call site, meaning that we can keep propagating through what the actual local late-bound type is, and don't lose the information like we do here. And we can say, okay, D arrow foo, that works, it returns this. This is a D here on the last line, and you can call bar on D, and all of this works. Next feature, loop fixed point. Variables can change types in loops since variables aren't declared, and this is an enormous amount of fun. So here's an example bit of code. This might look a little bit contrived, but I promise you this is a simplification of code that was actually given to us by a product engineer in the early days of Hack, that we were mistyping this code. So this is a realistic example, believe it or not. So should this be an error or not? What happens here? So x, y, and z are going to be initialized to ints, but if you notice I have this chain, z becomes a string, and depending on how many iterations at runtime I go through this loop, the types of these variables, maybe int, maybe string. Z actually might be an int if I go through this loop 0 times. So how do we deal with this? What should the type of x be? The type of x should probably be unresolved of int string. But doing this naively, you've sort of got to, when you're typing this code, you've got to recheck this loop, continuing to look at what because the types of the locals when you come out of the loop recursively depends on the types of the locals going into the loop. And so you've got to keep checking this loop over and over and over in order to make sure that you propagate those types forward the right way. You've got to, in fact, iterate it until you hit a fixed point. And that's exactly what the Hack type checker does. We can actually calculate a priori how many times we're going to need to do this in order to hit a fixed point. That makes this a lot simpler. You can look at the chain of assignments. We can see z goes to y goes to x is the longest chain, so we need to hit this 3 times. And we can iterate over the loop, take the types of the locals over each iteration, and then it's unresolved of that at the end. Nested loops make this even more exciting. That was actually it turns out, one of the biggest performance bottlenecks in the type checker. We were spending something absurd, like 10% of the entire startup cost of the type checker was dealing with like 3 call sites of nested loops that had really long chains here. And thankfully, one of our new hires was great, changed this from an exponential algorithm into something that's like quadratic and saved a whole bunch of time. So yeah, that was fun. Nested loops are fun. This is still a little bit of a perf issue, but it's surprisingly important. It comes up in places you wouldn't expect. It's important we get this right. So something else that's a perf issue, and as a matter of fact ended up being such a perf issue that we couldn't add this feature, is intersection types, which is idiomatic code causing variables to have more than one type. That's a mouthful, so let me just jump to the example. Again, we don't have this feature. This code is currently in error. So let's look at this. We have 2 interfaces, I1 and I2. And I1 implements foo, I2 implements bar. We have a function f, which takes something that's an I1. And I call x arrow foo on it, which I should be able to do, because foo is defined in I1. Now my x might also be an I2. The interfaces aren't mutually exclusive. So I should be able to say, if x instance of I2, call bar on it. The instance of will change the type of x, and so far that's exactly what happens. X is an I1 here and an I2 here. But we fail here on the last line. You should still be able to call x arrow foo here. Like, the type of x hasn't actually changed. It's still going to be at least an I1. But we don't know that. So what happens here? Why does this fail? Remember what I was saying earlier about if-else blocks and unresolved. The type of something coming out of an if-else block is unresolved of the types that it had inside the if-else. And so inside the if, the type of x is I2. Inside the else, the type of x is I1. You can sort of think of there being an invisible else block here that's empty. And so, when we come out, the type of x is unresolved I1, I2, and you can't call foo on an I2. This is kind of silly. We shouldn't be forgetting information like this. What we would like to do is say, inside the if block, x is not just an I2. It's an I1 and an I2. It's an intersection of the both. We use an intersection type there. And then when we come out, we can say x is unresolved of I1 and intersect I1, I2. And so things have to work on every unresolved, but when you hit the intersection of the unresolved, it can work on either of them. But if you notice from sort of the mouthful way I just described that, you can think of this sort of as like plus and times unresolved and intersect distribute over each other, which is why this is such a performance problem, and which is why we can't do this, and we currently get this code wrong. And we emit an error here when we really shouldn't be. This is a pain in the butt. I wish it weren't such a performance problem. This is probably the #1 ask from Facebook front-end engineers is to fix this, but we haven't come up with a solution yet that we're happy with, that's sound, and that performs well enough, in particular that doesn't involve types that distribute over each other, causing performance problems. So one last thing I want to talk about before I go on to the actual implementation of the type checker is error messages. We need to tell a good story when things go wrong. Some languages you might be familiar with. In particular, I write a lot of OCaml, since the type checker is written in OCaml. Not known for their error messages. And so we really want to tell a good story with our error messages. So let's look at this code. This is going to be a type error. I have a function f, and depending on which condition I hit, this x is either going to be an int or it's going to be null. But I return this potentially null int as a non-nullable int. And so this is a type error. This could be null. So what does our error message look like? Our error messages are going to come in 3 parts. The first thing we're going to say, okay, invalid return type. Here's the red arrow. This is where your error is. This is what doesn't work. But we also keep witnesses for what types we're trying to unify here, what we're trying to make compatible. And so we can point at where those things don't work and where they're incompatible. In particular, we can say, well, you wrote int here in the function signature, and it's incompatible with a nullable type, and well, here's where the null is that makes me think this is a nullable type. So we can point the programmer directly at the incompatibility so the programmer can go and fix it, as opposed to just saying, this don't work. Here's a more complicated example. This is a generic class. This is a box. It's got a constructor that's going to take in something of type t, which is the type that's parameterized over. We're going to call that x. This private t $x syntax is going to write it into a member variable. This is called constructor argument promotion. Don't worry about it. Just know that this arrow x is defined. It's written to. It's going to have type t. This get function works. This function f is going to try and use a box by putting an int into it and getting the int back out. But of course, I've written string here. This is going to be an int, not a string. This is going to be incompatible. So I'm going to have a similar sort of error message. And we're going to say, okay, you have an invalid return right here. You wrote string, and it's incompatible with an int, and we can point at exactly where we inferred that this must be a box of int, as opposed to a box of string or a box of anything else. Here's the int, here's the witness, here's what went wrong. Even through stacks of generics and other things feeding into other things, we can point at where the incompatibility originates, walk you through what was going on, and at least I think provide a really good trace of what's going on and help programmers continue to be productive and fix their problems quickly. Error messages aren't just about witnesses for types. They're sometimes about explaining edge cases of PHP. Here's a fairly interesting one. We're going to divide these 2 integers in PHP, or in Hack. The semantics are the same in PHP. It turns out that integer division in PHP and Hack can return either an int or a float, depending on if the division was even or not, or divided evenly or not. So this is invalid. This isn't always a float. It could be an int. And so our error message would point that out. Invalid return type. This is a float. It's incompatible with num. It means int or float. And it's incompatible, and I said num because it's the result of a division. Not only do we keep witnesses for all the types, we keep reasons for why we thought something was that type. So we can point it out when it's not necessarily obvious how we thought this would be num instead of int or float, if you're not familiar with this particular rule of PHP. Okay, so there's a bunch of time talking about some features of the Hack type system. Now I'm going to talk about the actual implementation of the type checker that actually enforces this type system. Scaling this thing is really interesting since at Facebook scale, tens of millions of lines of code. We need to be fast, have the fast iteration cycle that I said at the beginning that PHP has and not compromise that. So how does a type checker actually check code? One of the most important things about the checker is the way that it checks code is divided into phases. Parsing, global environment, naming, declaration, and typing. Parsing is actually reading the files off of disk, building up an AST, the sort of thing that you'd expect out of parsing. Global environment is a quick step that just says, is this thing defined or not? It generates a set of everything that is defined, all the classes and all of the functions. Which we need during naming, in order to resolve names, determine that you're referring to something that exists, and massage the AST into something more useful, or something easier to work with, not more useful. Declaration builds up a signature for everything, so that we can do our everything is one step away. You only have to look at the declaration in order to do typing, which is actually doing the type checking. That's sort of a lot to go through. The exact details of what's going on everywhere here is not super important. If you have questions at the end, I'm happy to go through this in more detail. But it's broken up into 5 phases. And one of the important things of the phases is that data to, for example, do typing. When I'm doing typing, I don't need any data from other functions that are being typed. All I need is data from declaration. Declaration builds up these signatures of what the inputs and outputs of all the functions are, what classes look like, what their member functions look like, what their inputs and outputs are. So to do typing, that's all the information you need. You don't care about the type checking of other functions. You care about just their signatures, since everything is one step away. And so you only need data from declaration when you're doing typing. And that's in fact true of all of these phases, meaning that we can multi-thread it. It turns out computers have lots of CPUs and code has lots of functions, and so that's a really convenient unit in order to multi-thread in. And so the phases were carefully designed such that this was tractable. Bootstrapping the type checker on tens of millions of lines of code would be hopeless otherwise. So multi-threading. I've been saying that the type checker is written in OCaml, so this gets exciting. We can look at these phases as synchronization points, but we've still got to deal with how do you do threading in OCaml. So, yeah, that's actually a really interesting problem. OCaml threads are hopeless. People that have done OCaml, completely hopeless. The model's just wrong. Also, OCaml has an aggressively single-threaded GC. And so, that's not going to fly. You're going to have everybody, always being locking everybody else when you're doing any sort of allocation, which is everywhere. So that doesn't fly. Okay, can't use threads. What do you do instead? Well, you can fork. That's how you get multiple processes going. So, okay, you can have this type checker. It can fork a bunch. But now, instead of everything being shared with threads, everything's separate when you've forked. So how do you multi-thread and coordinate all of that when you have all these different processes that have all forked like this? Sort of the obvious answer to that is using some form of inter-process communication. Unix domain sockets, pick your favorite one. We did that for a while. It turns out you can build a type checker and that'll work. You can multi-thread it that way, have everybody talk to everybody else over Unix domain sockets. It turns out that's really slow. You end up serializing, deserializing, copying in and out of the kernel and to and from all of your processes, all sorts of data all the time. We have tens of millions of lines of code. These data structures aren't small. And serializing them over these sockets is not really what you want to be doing all the time. So what do we do instead? It turns out, for those of you that are intimately familiar with Unix internals, there's a couple of flags to the mmap system call. Map shared and map anon. I won't go into the details of what exactly the semantics of them precisely are, but the gist of it is you can say, hey kernel, give me this block of memory, and mark it and map it such that whenever I fork, I want the same physical frames mapped into each of my child processes when I fork. That means that writes in one of the child processes are visible in this area in all of the others. It's not copied like most pages are whenever you fork. And so this is what we use. We have this area that's shared between all of our processes. We bring up the original type checker process. It maps this area, then it forks once for each CPU, and now they're all sharing this giant shared memory region between them, even though they're separate processes. So what's actually in this shared memory region? It is a shared lockless hash table. We've got OCaml, shared data structures, and lockless data structures. Now we're getting really exciting. So one of the key things that's going to make this, I'm going to go into how we manage this and don't manage to blow our feet off. One of the key things to keep in mind is since we're computing a bunch of type data, the data is all immutable. Once we compute the signature for a function, it's not changing. Our type checker works incrementally, which I'll talk about a little more in a minute. So that means that we might need to, delete the signature, recompute it, and reinsert it if the code is updated. But we're not actually mutating the data in the hash table. And so that makes this whole thing, again, one of the careful decisions that was made to make this whole thing tractable at all. Okay, shared lockless hash table. Yeah, segmentation faults, that's the sort of thing. This gets really exciting. I wouldn't want to express code like this in anything except for C. Certainly not OCaml. And it turns out that's what we do. we have this giant wad of C code linked into our pretty OCaml type checker that manages this shared lockless region, this shared hash table. Thankfully, OCaml has a really nice foreign function interface, so as far as OCaml is concerned, it's just some function that you're calling. And again, makes this whole thing tractable. So how do we actually manage this shared hash table? We have a bunch of really nice invariants that, again, make the whole thing hang together. These invariants might sound specific to the Hack's type system, but it turns out they're actually fairly general. We have another piece of software called Flow, which is a type system for JavaScript. And its type checker is actually built on a lot of the same core code as Hack is. It uses our same implementation of this lockless hash table. And so these invariants generalize fairly nicely to a surprisingly wide variety of different applications. So first invariant. Only one thread or one process, I'm going to use thread and process interchangeably from here on out. Only one thread will ever be deleting from this hash table at once, and nobody else will be reading or writing whenever it's doing that. We just coordinate the master and the workers such that this happens, and having this invariant means that we get rid of a whole host of really nasty issues with lockless data structures. For those who have studied any sort of lockless data structures, it turns out one of the most difficult things to do is dealing with concurrent deletes with anything else. And so we just say, no, heck with that, not going to happen. We've engineered the system so that that won't happen. We're not going to worry about it. Gets rid of a whole host of nasty issues. Another nice invariant we have is that if we have concurrent readers and writers to the same slot in the hash table, then it doesn't matter who wins. The reader may or may not see the data. It may see that the slot's empty. It might see this data. But it doesn't matter. All of our functions generate immutable data. All of the functions, the typing functions in the phases are all idempotent, meaning that if data isn't there that should be, we're just going to go off and recompute it. It's a potential performance problem if this happens a lot, but it's not a correctness one. We can always go recompute data that we happen to not see, even if that data is being concurrently written. This makes things fairly nice to work with. You just sort of like can shove something in there and, well, maybe you see it, maybe you don't. Not a big deal. Now, folks that have been really paying attention here might be wondering when this can happen. When I was talking about the phases, I said that a phase never needs data from within the same phase. You're always reading data out of the last phase. So when does this happen? I should be reading from one slot and writing into another slot during a given phase. I should never have somebody reading and writing from the same slot. It turns out that what I said about the phases isn't quite true. And here's why. I talked about one of the phases, phase 4 was declaration. It needs to build up all of the signatures for classes, all of their member functions and member variables. And in particular, it needs to do compatibility checks with parents, and it needs to, for performance reasons, inline all of its parents' signatures so we don't have to potentially walk up a long inheritance chain. We need a method, when we have a subclass and need a method in the superclass. That means that we need to declare superclasses before we declare subclasses, and so we actually do have a little bit of cross-phase data needed. In this example, cat and dog both need mammal to be declared first, mammal needs animal to be declared first, such that mammal can inline the information from animal, and cat and dog can inline all the information from mammal and above. So this is when you can get concurrent reads and writes. Let's say we start declaring cat. Cat is going to say, mammal hasn't been declared yet. I'm going to go declare mammal. Dog starts going to declaration. Dog says, I haven't declared mammal yet. I'm going to go do that, just as cat starts writing the data in. Oops, dog may or may not see the data that cat just computed. Doesn't really matter. Dog's going to go off and recompute it. Again, an unfortunate performance issue if this happens a lot, but not a correctness one. Dog can always go recompute mammal. Okay, so since we do actually have a little bit of this interphase pollution, you can have simultaneous inserts if cat and dog both go recompute mammal and go try and insert the data at the same time. But again, they've recomputed the same data. It's idempotent. It's immutable. One of them arbitrarily wins. Doesn't really matter who. And so you just pick one. Whoever gets there first, that gets written. The other one might overwrite it, whatever. One of them wins arbitrarily, not a big deal. One very, very subtle invariant that we need to maintain, and that we didn't realize for a long time we needed, is this one. If a single thread writes data into the hash table. It needs to be able to read that data back out. If we have this sort of insert read that I had a couple slides ago, I said the reader may or may not see the data for some arbitrarily long time forward. That's true for other threads. The thread that wrote it needs to be able to see it. When cat goes and sees that mammal hasn't been computed yet, it's going to go compute mammal and write that in, and then go do cat. It had better be able to read the data for mammal that it just recomputed. We didn't have this invariant for quite a while. We didn't realize we needed it. And it would manifest as this very subtle bug where very occasionally you would have subclasses that would be missing methods defined in superclasses. So we had to go add this invariant. My favorite part of this anecdote is that fixing this involved a little bit of a memory barrier in our C code. So our nice, pretty OCaml type checker has an ASM volatile line buried deep in the bowels in order to fix this bug. That was a lot of fun. So I've been talking about how we parallelize the type checker in order to make type checking fast and get that fast response time. But even with parallel computation, that's not enough. We need this fast iteration cycle of PHP that I was talking about at the beginning. We need to preserve that. And so even a 5, 10, 15-second type checking time is not enough. We need 100 milliseconds. So how do we do that? We have incremental mode. We have this client-server model. Rechecking the code every time is too slow to get 100 milliseconds. We have tens of millions of lines of code, not going to do that. But it turns out, when an engineer is editing code, most code doesn't change. We can just go watch the file system via Linux iNotify in particular. See when a file has changed, the kernel will tell us. Go reread that file and recompute state based on that. We can have a server sitting in the background watching that happen. And so by the time you ask for type errors, we've actually incrementally updated our state. Everything's available in the background, and it takes 10 milliseconds to go talk to the server, ask it what the type errors are, and get them back. So how does the client-server incremental mode actually work? How do we know what to recheck? If I have some function f and it calls g and I change g, I might need to recheck f. So we need to track dependencies. The gist of it is that we type check function at a time. And since everything is only one step away, we don't need any sort of complicated recursive dependencies. Things don't propagate far in our type system. If f calls g, and I change the function g, if I change its signature, I might need to recheck the function f. But I don't need to recheck anybody that calls f. Only one step. Meaning that we can just record single-level dependencies. When I'm checking f, I see f calls g. We just have a little bit of code. When you go and look up the signature of g, we record, okay, I'm checking f, you looked up g, record that dependency. So now when g changes, we look at the reverse dependencies and can go in and update our state that way. There's lots of fiddly details, but the gist of it is really simple. For the most part, you don't have to worry about this. The core worries about dealing with fiddly details. It just records the dependencies as you look them up. That makes rechecking pretty straightforward. We know what all the dependencies are. G changes, we say, oh, reverse dependency on f, let's go recheck f. We just go and rerun all of the phases, update all of our state, update the hash table based on that, and it's actually pretty straightforward at this point. Okay, so that's the conclusion. I've talked about some of the features of PHP and Hack, how Hack has its pragmatism to keep the good things of PHP while still adding a type system and type check idiomatic code. I've also talked about how we, again, preserve the speed of the iteration cycle of PHP via incremental mode and this parallel type checking. You can see more details at hackling.org. There's a link to IRC channels, anything like that. It's all open source if you want to get involved or try it out. Thanks. I think we have some time for questions now. Yes. I think he's getting a mic.
So when you did the vector of undefined types, is
Yes.
there any point where you just give up and say you're messing with me? Because there's so many different undefined types in that vector? Or how do you handle that case?
You mean with the unresolved types?
The unresolved.
No, we will just keep adding and adding to the list. There is I forgot to mention this when I was talking about it. There's a really fun perf hack in there. We do an OCaml pointer equality whenever you're adding something into that unresolved list, which, again, for folks that are familiar with type systems, is like completely the wrong way to compare types. Types might have things in different orders, and have type variables. You just like can't do a pointer comparison like that. But it turns out that it's good enough for us to keep down the list of that, the length of that list to something manageable in most cases. Yeah, you usually don't build up a vector like that in code that we've seen into something super complicated before it hits some sort of type boundary, when we will collapse the unresolved into something that we know what it is then. So yeah, there are potential perf issues there. We don't give up. It's important to get it right, but they don't really come up in practice. We can work around them.
So I have a question. So you talked about AST, right, as the basic representation of the language that you're operating on. But
yes.
But based on your analysis, don't you need data flow analysis?
No, we don't. We need very, very basic stuff for conditioning the types of local variables, like my null check and instance of check that I was talking about. But you don't actually need to know where the variable flows, where it flows in and out of. You just say, okay, we have something that says if x instance of c. When you go in the if block, the type of x is now c. We don't have to analyze the flow of where x comes from or where it goes, just in these couple of cases.
So no linearization required at all? So still not...
If I understand what you mean, I believe the answer is no.
Did you consider, or maybe do you support const decorators on types?
We've talked about it a lot.
Because that might solve your problem of mutating the this pointer on that example. If that was a const method, then you could.
Yes, that is actually one of the cases. One of the shining cases for like read only or some form of immutability. We've thought about it. It hasn't been super high priority. We've had higher priority things to work on, so it hasn't gotten attention. The thing that needs to be spec'd out is how transitive it is. If I have a class that is said to be immutable, can it have, are its members mutable? How transitive does that go? Like if I have a class C that is a member variable that's of type D, and I say C is immutable, does D also need to be immutable? So on the one hand, you have like const in C++, which I believe says no, depending on how you write that const and where you put it. There's like different modes that you can write that. But it turns out that it might be useful for performance to insist that it is transitive, because there's clever things you can do with serialization and burning things into request state, like optimizations the runtime can make if it knows that it's fully transitive. I'm doing a poor job of explaining it, but you can imagine there's optimizations you can make on that. And so it's not really come to a point where we have to make a decision on needing this feature on sort of the ease of developers versus the performance trade-off for it. So we haven't built it yet. It hasn't been super high pri. But that's one of the reasons we haven't added it.
For that particular example, covariance is enough. If you can, for that particular example, covariance is enough, right? If you and we added that. So if you have a function and you know that the operations on the vector are going to be covariant, then you could relax the case that we've seen. But immutability is another way to get it.
Any other questions?
So when you're talking about that shared memory hash table,
yeah,
how often does that actually change in between various iterations of your software base? I mean, it seems like that's something you could just pre-compute.
Sort of, yes. So if what you're getting at is, so not only does code not change most of the code doesn't change whenever you're like sitting there writing on it. It turns out that most code doesn't change over time too. Is that what you're getting at? Yes. We actually have this project that is not completely open source. Bits of it are there, where you can start up the type checker at some known good state, dump out that shared memory region, and then restart the type checker with that shared memory region, and then you're up and running immediately without having to actually check your code. And you can use incremental mode from there. It also doesn't have to be the exact revision you're on. You can ask your source control system what's changed between where that state was generated and where you are now. We're actually doing all of this internally as of like 2 weeks ago or something. We turned it on. It's still pretty experimental, and lots of the bits of it, unfortunately, aren't going to be able to get open sourced, because a lot of it is like talking to a SQL database that like tracks when things are computed, does the actual computation on some sort of CI system. But the core of reading and writing the state that I just described, the code's actually there. I don't think it's documented anywhere, but the options are there if you go look for them if you want to try this. It's really fiddly to get right. It sounds simple, but it's really fiddly to get right. So I wouldn't recommend it unless you're Facebook scale. You probably don't need it either, but it's there.
Can you characterize your performance payoff? Just, I mean, in terms of code generation, and I know it's a big question to ask, but what's the gain?
You mean of Hack's type system?
Right. First, I mean, can you give us some war stories on pre-hack PHP code that runs like a top now that ran slow before? Kind of
so I can answer your question a little bit. I don't work on the JIT. But first of all, I want to like dispel some like memes I'm going on about Hack. Hack isn't about performance. It's kind of a nice side benefit in some cases, but Hack was about developer efficiency, having a type system that helps engineers fix bugs. It turns out the perf is sometimes a nice side benefit of that. I can't talk too much about it. I think experiments have been done. If Eugene is still here, which I don't think he is, he might be able to speak more to it. It is perf positive in a lot of cases. When you have a JIT, knowing that something is an int is a big deal. You can be stored in a register. Even knowing the exact type of a class is a big deal. You can avoid the equivalent of a vtable lookup and just burn the call directly in. However, the runtime still has to emit guards in order to make sure that something actually is the type that you say it is. The type system I've just described here, because of the interoperability with PHP, the missing annotations, it isn't necessarily sound. So HHVM has to do its own analysis. HHVM is the runtime. Has to do its own analysis, has to actually emit guards to check things at runtime to make sure they actually are, when you hit the function, what you said, before it can use this type information. Because if it's wrong, you're going to segfault. That said, there's more clever things where it can elide a lot of these guards. In a lot of cases, it's smart about it. So a lot of the perf payoff from the types comes down because of the guards. It ends up still being positive. I can't speak to the details of what, and I think none of the HHVM JIT folks are here right now to give you a more detailed answer. So I apologize for sort of hand-waving through that, but that's the gist of it.
Okay, one last question.
So I guess following up on that question then, do you have statistics on the correctness issues that you guys have caught? Like how, you know, certainly you've been tracking that.
Yeah, actually getting statistics on that is difficult, right? You don't know if a bug that you caught, you know, would have been a major issue 6 months down the line or not. It was fixed now. Anecdotally, we have lots of engineers that have come to us saying like, oh God, you caught this bug that would have been like, insert horrible bug here. You know, if this had managed to go to production, you like saved our butts. We've got a couple of war stories.
Didn't you have to like backport all of, so you took all of the PHP code and then you guys added a bunch of types there, and didn't you then detect a bunch of issues?
Sort of. Our conversion was done such that when there was an issue, we just didn't add the type annotations in a lot of cases, and it was up to the engineers to go and resolve those incompatibilities. We have tens of millions of lines of code. Like the three of us that were working on it at the time didn't know most of them. So automated tools can't really deal with that. But there have been places such as like Dwayne sitting next to you did a code change to deal with data fetching failures on one of our core data fetching abstractions. Found, what was it, like 1,000 places where people were missing null checks? Something like that.
Yeah, so it was probably closer to 2,000 or 3,000.
Yeah, and managed to like, through some miracle, like most of them ended up getting fixed, which is something that I think only Dwayne has had luck with actually doing that. Most of us have just put in like the, okay, this is bad comment, shut up the type checker, but actually most of those end up getting fixed. So there are other war stories that are, unfortunately, I can't talk about in a public forum, but yes, we do have them.
Cool. Okay, so I think we've reached the end of a talk part of this evening, so we're all going to be hanging out here for like the next hour or so, so I definitely encourage you to like find Facebook folks around, like ask any further questions you have.
Yeah, I'm happy to keep chatting for as long as you want.
And I'd like to give Josh another round of applause for thanking him.
Thanks everyone for coming. I appreciate it.
And I think we still have some like snacks and drinks at the back. Thank you.